In this video I will talk about the concept of center of mass. Now I'm gonna start with the figure. If I have, say I have one object here, another object there, another object there, and so on. Say this is the origin, this is the position of object 1, this is the position of object 2, this is the position of object 3, and say this is object 3, object 2, object 1, and you can think of those that they are let's say some balls, spheres of different size. So let's say this is 3, 2, 1, and each one of them has its own mass. Will be m3, m2. This will be m1. Now, if I decide on a coordinate system, so let's say that this is x, and that is y, and the z goes out of the board. Let's make this x and this y. As I said, z goes out of the board. This is my coordinate system. If I decide that the system, my system, includes everything, then I can calculate what I call the center of mass by doing the following calculation. I'm going to say that the center of mass depends on the positions of all three objects. Okay, so it does depend on those three positions. I have three objects, but if one of those three has a mass that is greater, then I want to give more weight to the position of that object, because that is a heavier object. So what I'm gonna do, I'm gonna say, okay, then I'm gonna assign a weight to every position, and that weight depends on the mass that I have at that point. Now this will allow me to say if m3 is much greater than the rest of the other two masses, then the position of object 3 is gonna have more weight in the calculation of the center of mass. And I'm adding those three. Now, because I want to keep I don't want the position of the center of mass, which is a position, to depend on how much mass I have total. I will divide this with the total amount of mass that I have in the system. So this will be divided by m1 plus m2 plus m3. So dividing with the total mass allows me to keep the position of the center of mass independent of how much mass there is in the system. It does depend on how the mass is distributed. If m1 is much bigger than the rest, then the position of 1 is gonna count more. If m2 is the greatest, then the position of 2 is gonna count the most in this calculation. But because I'm dividing with the total amount of mass in this system, I keep the calculation of the center of mass independent of the total mass. Now, another way to write the same thing is to say this is simply 1 over uppercase M, and with uppercase M I will just say that this is the sum over I of its mass. Okay, the Greek letter uppercase sigma means that it's a sum, and the I here indicates that I'm adding all the masses. So this really means m1, m2, and so on. Okay, it's a sum. So 1 over uppercase M means that you have 1 over the total mass in your system. And then if you see here in the numerator, I have a sum. So I'm going to use the Greek letter, the Greek uppercase sigma over I. I'm adding over I. I'm using this as my index. Mi, lowercase m, ri. And mi, ri essentially represent m1, r1, m2, r2, m3, r3, and so on. And because I have the Greek letter sigma, this means I'm adding all of those products together, the m1, r1, and so on. I'm adding all of those. So this is the definition of the center of mass. That's how you can calculate it. Now, I do want to point out this is a vector equation, right? So this is the position vector. And this here is also a vector. It's the position. Now, why do we use vector equations? I use vector equations because it allows me to write less. And in the same way, by writing less, I am indirectly or implicitly including more in this equation. So this is really 3 equations. 1 for x, 1 for y, and 1 for z. And those 3 equations are all included here in this single vector equation. So when you see a vector equation, it should really translate in your mind to 1 equation for every component. For example, if you want to find the, let's say, the x, if you want to find the x position of the center of mass, what you really need to do is 1 over m, and then you're adding I, mi, xi. See, so this is not a vector equation anymore. This is just about the x component. And you can say this will be 1 over the total mass, m1 x1 plus m2 x2, and so on. Okay. And you can do the same thing about y and z. But everything, all of this is included in this single vector equation about the center of mass. Now, what do I do if I don't have, in this example that I showed you, I had 3 discrete objects, 3 different objects, and I found their center of mass. What do you do if you don't have 3 discrete objects, but you have 1 that is a solid object? Let's say you have a cube, a rectangle, a sphere, a large sphere, or a pyramid, or any other shape. Okay, that is not that simple. When you have those continuous mass distributions, I will write it here. So this is what you get when you have discrete point particles, discrete points, discrete particles. Okay, this is the way to go. Now, when you have, let's draw a line. When you have instead a continuous mass distribution, for example, you have a pyramid, a cone, and it has a mass, and you want to find the center of mass of that object, then we need to divide the mass distribution to small pieces. And then I will model each one of those small pieces as a point particle, and then I will use the same process that I used before. Okay. Now, let me show you what how I'm gonna do that. So when I say divide my mass distribution into small pieces, I will say that each small piece has a mass of delta mi. Okay, delta because it's a small one. So now the center of mass, the equation for the center of mass becomes 1 over the total mass, and I have the first small piece that has a mass of delta m1 times r1 plus the second small piece that has mass delta m2 times r2, and so on, until I'm gonna keep adding this until I have the contribution from all small pieces of the mass distribution. Now I can write this in a more compact way. The sum of delta mi over ri. Now this calculation, so in this calculation, as I said, let's say I take, it's not really, let's say I have a pyramid, okay, whatever you want, whatever shape you have in mind. Now this is not 3D, but let's imagine that this is a 3D object. So I take this and I divide it into pieces. So this is piece 1, this here is piece 1, it has a mass of delta m1, then I have another piece, the second piece, that has a mass of delta m2, and so on, and I keep doing this until I have the whole thing essentially broken into pieces. Now I do want to show you, by doing this process, and this one here is 3, this one here is 4. The way that I'm really modeling this is the following. I have a point particle here, a point particle there. This is 1, this is 2, this is 3, this is 4, okay, and so on. So I'm really now, and this keeps going on, okay, I'm not gonna do all of them. So instead of, and then you have more, of course, over here. Instead of, so the way that I'm doing this calculation, the way that I'm finding the center of mass of this 3D object, is by really calculating the center of mass of a number of point particles. That's what I'm doing here, because I've broken this into pieces and I'm modeling each one of them as a point particle with mass delta m1, delta m2, delta m3, and so on. Now there is an issue here, and you can see that what I'm really doing here is not really exactly the same. Okay, one thing is to have a 3D solid object, one thing is to have just a bunch of point particles. It's not really the same thing, but I can make this calculation be closer to reality by making these pieces smaller and smaller. So imagine, let's see if I can show that. Let's see if I can show you that. So imagine that instead of taking that huge piece, I have this tiny one, and I have another tiny one, and I have another small one, and so on. Then I got one piece here, one piece there, one piece there, and so on, and so on. Okay, now I'm only gonna do, as I said, a few But now this is only the top, okay, so I'm only taking this part and I'm showing here. I hope you can see that this approximation, this model, is better than the one that I did at the beginning. The smaller pieces I use to do this calculation, the better it is, because the closer I'm getting to the actual 3D solid object. So then what I'm gonna do, I'm gonna go back to my calculations. I'm gonna say, okay, let's say that I can find the center of mass of a 3D, of a solid object, by using a huge number of pieces, and if possible, an infinite number of pieces. So what I'm gonna do then, I'm gonna say that the center of mass of that solid object is 1 over m when I goes from 1 to n, delta mi ri. So everything is the same as before, but now I'm gonna do the following. Let me erase this part. So it's the same as before, but now I'm gonna say the following. I'm gonna do this calculation when n becomes a very large number, and in particular I will claim that I will make n to go to infinity, because if n goes to infinity, I have an infinite number of pieces, which means I'm getting really, really close to the solid object, and this is how I can find the center of mass. Now, I hope you remember from calculus, when you have the limit of n goes to infinity of a sum that depends on n, this is what we call an integral. So, really, the center of mass is 1 over m of the integral. Now, I will mention here, when you have a discrete sum, you have delta m. When you have an integral, the delta becomes the d, okay, the dm, and I'm integrating over the entire mass distribution. So to find the center of mass of a solid object, you need to calculate an integral, really. 1 over m, the integral of r dm. Now, I do want you, when you see an integral in the calculation of the center of mass, I do want you to remember that the integral is really a sum where you have a very large number of terms, a very large number of pieces. And because we do have also one way to write this, it is easier to integrate over the volume rather than the mass. So I'm gonna do, I know that the mass density is mass over volume, so I can say here that dm is essentially the density rho times dv, where this is volume, and now I'm integrating over the entire volume, whereas before I was integrating over the entire mass. So this is rho, the position vector, this is the density, and this is the volume. And with this, I showed you how you can calculate the center of mass if you have a discrete set of particles, and how the same theory essentially gives you an integral if you have a solid object.